Good morning. My name is Xiaojie. I'm from the Electrical Engineering Department of the University of Washington. Today, I'm going to talk about a localization method and localization multiple access method for backscatter sensor networks based on synthetic aperture radar techniques. So I will talk about the application of localization in wireless sensor networks, explain our SAR localization approach, introduce our sensor tag design, and finally talk about a lab measurement of 2 sensor tags and analyze the results. The development of large-scale distributed networks is a significant scientific and engineering challenge, but it also shows great promise in a lot of applications. The capability of integrating the spatial information with sensing is crucial to exploiting the full potential of these systems. One example can be the smart warehouse, where the location information and the status of goods are both very important for logistic management. Another example can be the environment monitoring, when there is uncertainty in locations of the sensors. A lot of approaches using the signal strength, signal phase, and the signal time of flight measurement have been widely discussed. In our work, we propose a localization method based on coherent processing of both the phase and amplitude of all the backscattered data over a synthetic aperture. So SAR, the synthetic aperture radar, is a widely used technique in remote sensing. The motion of an antenna forms a large virtual aperture to obtain better resolution of the imaging area than available from the smaller physical antenna. So a 1D linear scan in cross-range direction of the imaging area can produce a 2D image including both the range and the cross-range information. So the radar transmits a wideband interrogating signal and receive the backscatter signal reflected by the illuminated point scatterers. Range information can be extracted from the impulse response of the cross-correlation between the transmitted signal and the received signal. So the range resolution is inversely proportional to the bandwidth. To obtain fine cross-range resolution, the energy transmitted by the antenna needs to be focused into a sharp beam, which can be achieved from a relatively long synthetic aperture. So to reconstruct an image of the scene in traditional SAR, we assume there are m point-like scatterers in the imaging area. So the received signal at each frequency of each aperture location is the sum of all the backscatter signal reflected by the point-like scatterers, giving consideration of the two-way path loss, the gain, and the measurement noise. So synthesizing all measurements over the frequency band and synthetic aperture, all data can be constructed into this form. This is the reflection coefficient matrix. And SAR reconstruction is the solution of the inverse problem. Rather than all scatterers being static, in backscatter sensor networks, a sensor tag can modulate the carrier signal with different modulation states. When 2 sensor tags each take 2 modulation states, the received backscatter signal can be any of the 4 possible values. If the data sending from the sensors is like the figure shown here, at time interval 1 and time interval 3, the only difference is the reflection coefficients of sensor 1. So if we follow the previously mentioned method to do reconstruction for time interval 1 and time interval 3, the subtraction for for the two reconstruction can give us the reconstructed location of sensor 1 with sensor 2 and other static scatterers being cancelled. Similarly, we can also get the location of sensor 2 or get the location of both sensors together. So the sensor tag design is based on a microcontroller driving a low-power RF switch that alters the antenna between two modulation states to form a BPSK configuration. The RF switch is based on this pin diode. The antenna we used were wideband bow tie antennas with a 10 dB bandwidth of more than 3 GHz. As for the microcontroller, we used the Arduino Nano for initial localization testing to emulate different sensor data at various bit rates. The Arduino Nano was directly soldered on the RF circuit board. The maximum bit rate of the sensor tag is limited by the Arduino Nano, which is 1 Mbps. The reflection coefficients of two modulation states measured at the antenna reference ports are shown on the Smith chart. So in the measurement, a closely spaced bistatic SAR configuration was adopted. The transmit antenna and the receive antenna were placed side by side on 3D printed holders that move along this linear stage. Two sensors were placed around 4 meters away from the linear stage. During the measurement, the computer generates different bit streams to the sensors, and a network analyzer collects S21 data at each aperture position while the antennas were moving. This figure better explains the geometry of the lab measurement. The locations of the sensors are shown in the table. The distance between the transmit antenna and the receive antenna was 10 centimeters. All antennas were 1.1 meter above the ground. The synthetic aperture was defined from minus 0.3 meter to 0.3 meter in 4 millimeter steps to avoid spatial aliasing. During the measurement, the network analyzer generated a 10 dBm continuous wave signal to the transmit antenna and measured S21 over 10 to 13 gigahertz in 10 megahertz steps for 4 times at each of the 151 aperture positions. So we first reconstruct an image of the measurement environment. So the reconstruction area from cross range minus 0.3 meter to 0.6 meter, range from 3 meter to 5 meter. So we can see the cluttered environment contains countless reflectors and scatterers. So where are the sensors? How can we detect them? Use the method I just mentioned. When the data sending from the sensors is like showing the figure, we can do a reconstruction for time interval 1 and time interval 2. The subtraction of these two reconstruction can give us the location of sensor 1. Similarly, subtracting the reconstruction of time 1 and time 2, we can get the location of sensor 2. What if we want to get the location of both sensors together? Just find 2 time intervals during which the reflection coefficients of both sensors are different. Compare the measurement results with the tape measurement. We can see the errors are within 3 centimeters. Scaling the point spread function to minus 3 dB, the measured resolution, they agree very well with the calculation. To sum up what we've done, we have demonstrated the use of SAR for sensor tag localization at X-band. Each tag can be either localized separately or in combination with other sensors. Fine resolutions were achieved with errors of less than 3 centimeters. Future work includes a fully designed sensor tag, a low-cost transceiver, and the software prototype. Thank you.
Thank you.